Hello students, in the last lecture we have found out the expression for the gain coefficient gamma and we got this expression. So in the next topic also we will come back to this expression itself, okay, and the next topic is nothing but line shape function. So over here we have to just talk about how the line shape function, like a bell shape function, and how it is important, correct? So over here we have seen till now that the emission of light by all atoms is monochromatic, and the frequency basically is given by nu 0 is equal to E2 minus E1 divided by H. But actually, correct, this is the frequency, but actually the light emitted by an atom is a burst of decaying exponential. Now what do you mean by burst of decaying exponential? It is this way. So I can show you. The graph will be like this, and then it will start decaying in this fashion, okay? So I can say this pattern, clear? So the actual frequency, what we said, of light centered at nu 0, this we are going to talk, and this has got a spread over a certain range delta nu, which I'll show you over here. Suppose I plot a graph of intensity I versus nu. This is my nu. So here I will be able to show you the bell-shaped curve like this. So exactly at the center, I am drawing without a scale, okay? So this is my nu 0, what I had spoken just now. So this is nu 0. Exactly in the center I will show this is my I by 2, this is also I by 2, and this part we will join it over here. This will give me this will be my delta nu. Fine. So this is my intensity versus nu, and this is nu 0. So what we said, that the actual frequency of light centered at nu 0 has spread over an entire range delta nu, correct? Now the Fourier analysis of decaying light, what expression we wrote? Decaying light shows delta nu is approximately equal to 1 upon tau sp. This already we have seen it. Now delta nu is what? Is line width, correct? This part delta nu is line width. Line width, which is defined as, now we need to define this value. So it is defined as frequency difference corresponding to intensity half I. This is also I by 2, this is also I by 2. So we can say line width is frequency difference corresponding to intensity half of I. Fine. Now similarly, what we said, that the atoms are capable of absorbing light not just at single frequency but over some band of frequencies, correct? So what we can say, that the shape of the curves is described by the topic line shape function, which is given by G nu. So the function G nu is usually normalized according to condition. So I'll write down the equation over here. Integral minus infinity to plus infinity G of nu d nu has to be equal to 1. This is my line shape function, G nu. So G nu d nu is basically what we say, the probability that a given transition between energy levels E2 and E1 will result in emission of a photon whose frequency lies between nu and nu plus d nu. Fine. So what happens basically? A photon of energy h nu may not necessarily stimulate another photon of energy h nu. So radiation density, last time we have seen the expression, radiation density rho nu d nu incident on collection of atoms has frequencies between the range nu and nu plus d nu, and out of total n1 and n2 atoms per unit volume, fine, only n1 g of nu d nu and n2 g of nu d nu atoms per unit volume are capable of interacting with radiation of frequencies lying between the range nu and nu plus d nu. So the expression what I got in the last lecture, I wrote this expression. So gamma, so before this we'll talk about the expression where we put the values. So this one. So if gamma is n2 minus n1, so instead of h nu I'll write h nu 0. So I'll say equation number 23 from the last derivation. So I'll say gamma is equal to n2 minus n1 into h nu 0, fine, into b12 divided by v. Correct? So we know b12 is equal to b21. We have the value ready with us. So if we say b12 is equal to b21 is equal to, what is the expression? C cube, already we have it over here, C cube divided by 8 pi h nu cube correct, into mu cube into A21. Fine. So if you substitute this value in this expression, okay, and we know the value of A21 is how much? A21 is 1 upon tau sp. So if we substitute that, what we got the expression last time, we got the value gamma is equal to, same thing what I am doing, I will not repeat it again. I'll just put the value of b12 and I'll put the value of A21 and I write the expression. So here I will get the value of gamma to be, which is my gain coefficient, is equal to n2 minus n1 into v square g nu divided by 8 pi nu square into tau sp. Fine. And this nu 0 is basically the central frequency which is shown over here in my line shape function. Line shape function is g nu, g of nu. Nu is the frequency given over here and nu 0 is my central frequency. That's what this smallest topic wants to give the information. Now we'll move towards again a very small topic but again very important, so which is population inversion. Population, very very interesting and very very important. Population inversion. Now here we need to define first what is population inversion. So what we can say that when an atomic system is in thermal equilibrium, very very important word, thermal equilibrium, what happens? The photon absorption and emission takes place side by side. Moment you say that you have energy level E1 this is energy level E2. You say that the absorption, emission keeps on happening side by side. But as N1 is greater than N2, okay, all the atoms would love to sit in the ground state. So that's why N1 is always greater than N2. So absorption dominates, correct? But what we want the laser operation. So for the laser operation, what should happen? Laser operation requires stimulated emission exclusively. If that is not there, you will not get the laser operation. So what to do to achieve this? What do you need to do to achieve high percentage of stimulated emission? A majority of atoms should be at the higher energy level E2 than at the lower energy level E1. So which means I want N2 to be greater than N1. Correct? So the non-equilibrium state in which the population N2 of the upper energy level E2 exceeds to a large extent than population N1 of the lower energy level is basically known as population inversion. I'll repeat this. The equilibrium state means when N1 is greater than N2. But with this, what will happen? There will not be any laser operation. So to get a laser operation, what you need to do? You need to get this. How it is possible that the non-equilibrium state will occur? This is equilibrium. Now we need to do non-equilibrium. So the non-equilibrium state in which the population N2 of upper level energy level E2 exceeds to large extent the population N1 of the energy level E1. This is known as population inversion. So now, extending Boltzmann distribution to this non-equilibrium state of population inversion, it is seen that N2 can exceed N1 only if the temperatures were negative. So very important condition. Temperature must be negative, because if it is positive, you can't get this. You always will get this. So temperature must be negative, and therefore population inversion is also known as negative temperature state. Correct. Now to understand this, we'll just show you a simple diagram. So suppose here I have my 3 states. Okay, so this is first my E1. Here I'll show my E2, and here I'll show E3. Fine. So here this I'll show it by this small part. E2 will be little bigger. Okay, and the N1 is far bigger. So this is N1, N2, and this is N3. So I can join them this fashion. I can just show these states in this fashion. So my y-axis is energy axis, and this I'll say number of atoms in a particular level. So now what can I say? That consider a system that has got 3 energy state. 3 energy states. Which one? E1, E2 and E3. Fine. So now with the system in equilibrium, the uppermost level E3 is populated least and E1 is populated the most. Correct. So the population 3 state will be given by what? N3 less than N2 less than N1. So the system absorbs photon rather than it emits photon. So if system is supplied with external energy, because this is normal, as I mentioned, N1 will be greater than N2, N2 will be greater than N3. We do not want that. What we want? We want N2 to be bigger than N1. So what we need to do? If system is supplied with external energy because we want to observe larger stimulated emission. So we'll have to supply external energy such that N2 will exceed N1. And what we can say that the system reaches population inversion, and the population inversion taken place between E2 and E1. So how we can show that? So again, this is my number of atoms and this is energy. So over here, what will happen? First I'll show E1. So E1 will be, this is N1. I need to show my E2 is going higher and E3 as it is, not much change. Fine. So this is N3, N2, N1. So what I expected, N2 greater than N1. Why? Because I supplied external energy. Okay? So I achieved that. So now under the condition, I'll just draw this to get the same effect what we had earlier. So now under this condition, the stimulated emission can produce a cascade of light. Why? Because we supplied energy and we achieved N2 greater than N1. So we'll get cascade of light, and the first few randomly emitted spontaneous photons trigger stimulated emission of more such photons, and those stimulated photons induce still more stimulated emission, and this will keeps on going. So as long as excited state population is more than the, as far as this N2 is greater than N1, okay, stimulated emission are more likely than absorption, and therefore light gets amplified. Okay, light has to get amplified continuously. This we can show it in a simple diagram. So suppose this is my medium. So here I can see I have to get N2 greater than N1 to get the light. So suppose here I passed my input wave. So input wave is going, I am trying to get N2 greater than N1. So this I can show you in this fashion, and moment this is out, it will be in this fashion. So this is my output, this is my input, and this is N2 greater than N1. And then here I have more population, that is called as population inversion. So as soon as the population of lower level becomes equal to, which means when N2 tries to come down to N1 or lesser than N1, correct? As soon as population of lower level becomes equal to or larger than that of the excited state, correct, population inversion will stop and stimulated emission will completely diminish, and the amplification of light will not continue, or amplification of light will completely get ceased. So this is the way we can show it diagrammatically, how you understand the simple term but very important term called as population inversion or the negative temperature state. Usually you get this, but to achieve N2 greater than N1, that is non-equilibrium state, is possible only when you have the temperature to be negative. So initially this is the normal case, but we do not want to keep on checking how much is absorption and how much is emission. We want to give energy and expect this happens. So this will happen means when N2 greater than N1, definitely you will be able to see the cascade of light. And when you see this will keep on repeating, the emission of more and more spontaneous photons will keep on repeating, and you will be able to see the laser light out of the medium. Okay, so this what is very important term as far as population is concerned. Now one more small concept I'll say, which is called as pumping. Now, what is basically pumping? You need to maintain the state of population inversion, which is very, very important. To maintain the state of population inversion, which means maintain what? N2 greater than N1. It is necessary to promote atoms continuously from lower level to the excited level. N2, this is E1 and E2. What to do? Promote atoms continuously from lower level to the excited level, and energy is to be supplied to laser medium to raise atoms, and for maintaining population at excited level N2 greater than N1 at higher value than that of the lower energy. This process of raising atoms from lower level to upper level is basically called as pumping, which means if pumping is not there, you cannot maintain the population inversion. So you want the laser light to be out, you need to do proper pumping. Proper pumping means to maintain the state of population inversion. That's why this pumping term is very, very critical for the laser action happening properly. Now there are many methods of doing this pumping. The first method is called as optical pumping. Second one is electrical one. Third is X-ray. And the fourth is chemical. Now details of that I will take it little later. I will not waste time in this. I will directly go to the 2 level and 3 level schemes also, or basic definition of active medium, metastable state, and so on in the next lecture. But this is must. That's why I thought I must at least mention about it, that why do you or how do you maintain the state of population inversion? By keep on pumping the atoms from lower level to upper level continuously. Okay, and this process of raising atoms from lower level to upper level itself is called as pumping, and these are the various methods by which we can achieve the pumping properly taking place or maintaining the state of population inversion. Clear? So we'll stop over here.